So our first speaker is Eleanor Knox, Philosophy of King's College, London. Eleanor studied physics and philosophy in Oxford with Harvey Brown and David Wallace, then did a few postdocs. The Leverhulme, that's how we pronounce it in Dutch.
I never knew.
It's not even Dutch, but that's how I'm going to pronounce it anyways. She was a visiting scholar at the Perimeter. She was a visiting professor at in the HPS department at the University of Pittsburgh. And of her many awards and distinctions, I just wanted to single out that you won the Cushing Memorial Prize for the best article by a young philosopher of physics. And Eleanor is going to talk today about like space-time functionalism and non-commutative gravity.
Oh, microphone. Can everyone hear me? Good. Too many hands. All right, so thank you so much to the organisers for putting this on. Needless to say, it's been fantastic, although late night dinners in Abbey aren't necessarily good for the quality of your talk this morning, but hopefully we'll get over that. Okay, so what I want to talk today about is one thing I've thought lots about, namely space-time functionalism, and another thing I've thought very little about, namely non-commutative gravity. So what I'm going to do today is try and outline this kind of view that I think is a good way to think about space-time theories called space-time functionalism, and this particular variety of it that I like when we think about the inertial structure of theory in order to work out its space-time structure. And then I want to say some very tentative things about how this kind of thing might be useful when applied to non-commutative geometry. There are probably people in the audience, certainly people in the audience, who know infinitely more than I do about non-commutative geometry. So I'm not even pretending to be an expert, not pretending that I think it's the best model for quantum gravity, but it's intrigued me for various reasons, so hopefully I can at least sort of share what's intriguing me about it with you, and perhaps convince you that my way of thinking about space-time theories might be helpful to this kind of theory. Okay, so I'm going to start with a sort of philosophical prelude, which we'll see if that goes down well. It's not something I would normally do, but someone suggested that it was required before I talk about space-time functionalism, so I'm going to do it. And then I'm going to tell you what this theory is, this space-time functionalism, tell you my variety of it, and then give a very, very rough sketch of what I think is going on in non-commutative geometry, and one sort of answer some questions about it that I think are interesting. Okay, so here's the rough philosophical sketch. What I'm about to do is cover 50 years of debates between very complex places between smart grids and 2 slides with a couple of images. This is sort of meant to situate philosophers in terms of what I think I'm doing, and maybe it's helpful for physicists as well to make some comments about what we might do as philosophers. But here's the question. What are philosophers good for? Right? They're just drinking buddies, they organise excellent conferences, but I think we do lots else besides. But there's one kind of role for philosophers that's sort of out of fashion now, and this variant is rightly out of fashion, but it says that what philosophers do is something called conceptual analysis. And one of the things that philosophers do is they look at concepts and they discover substantive a priori conceptual truths. And then a sort of really old-fashioned and wrong way of thinking about this is to think that, on that view, philosophers assert something like meaning postulates. They find the once-and-for-all meanings of the terms in our theories. And then once we fix the once-and-for-all meanings of the terms in our theories, we can get on with doing precise physical theorizing. Now, anybody who's done kind of philosophy of science, philosophy of language, or any kind of philosophy 101 is going to know that we don't really think that we do that anymore. Various arguments undermined that. But one of the things that sort of happened is that maybe we stopped talking about concepts altogether when we threw out this kind of very, very strict role for philosophers. And there's a kind of more modest role that you can think of. So one of the things you can do is acknowledge that one of the major problems with this idea that philosophers defined the concepts in your physical theories once and for all was that it fails to take into account the fact that concepts and words and terms in science behave in funny kinds of ways. They're shifty, they move around, and they move around not just between theories, but between different contexts within a single theory. So one of the problems with anything like giving definitions is that you're just hopelessly hostage to fortune because terms don't sit in one place. They shift. So if you think about a term like entropy, or kinetic energy, or force, and you think about how that's been used in successive physical theories, you'll instantly see that, on the one hand, there's not a complete discontinuity from theory to theory, but if you decided to define kinetic energy as a half mv squared, you would have a great deal of trouble making sense of what Einstein did, or think about the kinds of things that are happening with entropy in black hole thermodynamics today. It's clearly a concept that's shifting, right? And we have to be able to account for that. But just because things shift around doesn't mean that we don't have to keep track of them at all. It's still the case that even though these kind of explicit conceptual considerations are largely out of fashion, a lot of what we do as philosophers is trying to kind of keep track of what people are saying about their theories and work out how to make sense of them in light of the kinds of associations that we have with concepts in the past. And if we let our concepts move around completely and you just scatter them around, you have kind of meaningless, unhelpful things being said about your theories. So there's still lots of good conceptual work to be done, both in tracking and understanding how concepts change, and in making sure that we're not importing old conceptual assumptions in places where contexts where they don't quite work. So a more reasonable view sees the philosopher not as a kind of conceptual stipulator or judge, but as a conceptual housekeeper. Now, Jeremy Butterfield was the person who told me I needed to say this at the beginning of any talk on space-time functionalism, and he told me I should describe myself as a conceptual housekeeper. And I explained to him that no woman in the philosophy of physics could self-describe as a conceptual housekeeper. But at least I found some male janitorial clip art, so that's a little bit better. But nonetheless, conceptual housekeeping is very much sort of the right word for the kind of thing that I want to do. So I think conceptual housekeeping is really important in the case of space-time theories. If you're trying to keep track of space-time structure in your theories and think about different theories and think about the kinds of things you might want to say about space-time in different theories, it's particularly important to have a think about how you're using the space-time concept. Because space-time is a really important concept in our theories. It comes with automatic empirical assumptions, so it kind of has this empirical significance built into it in lots of scenarios. It's really important for getting predictions out of our theories in terms of, say, times and distances. And so if you're not a little bit careful about what you're calling space-time or how you're talking about space-time, you could easily import assumptions that don't quite fit in a new context. It's also true that theories of quantum gravity are generically pretty pathological when it comes to the space-time concept. They generate all kinds of different geometrical structures, non-geometrical structures, and you have to try and work out what to say about space-time. And a lot of what gets said about theories of quantum gravity are substantive things about saying how space-time concept applies in some quite distant context from the kind that we're used to. So if you want to talk about emergent spacetimes or discrete spacetimes or spacetimes with many more dimensions than 4, it's not that you shouldn't do those things, but you better be a little bit careful about what you are and aren't continuing, what assumptions you are and aren't importing from our familiar spacetime contexts. So this talk is in many ways an exercise in housekeeping. And here's my favourite housekeeping principle, spacetime functionalism. Spacetime is a functional concept. That is, a field or object is spatiotemporal by virtue of playing a certain kind of role in our theory. The slogan is spacetime by virtue of what it does, not what it is. As it stands, this is just a kind of heuristic, right? It's kind of a general way of thinking about how we should solve these kinds of problems. Until I've said something about the functional role, I haven't said very much at all, but I also want to really defend this kind of heuristic. In fact, I'm sort of most attached to this heuristic, and then the particular functional role I think is interesting can be debated. But I do really want to defend that this kind of way of thinking is the only way we ought to be thinking about these sort of strange scenarios like quantum gravity. So what kind of thing are you committing yourself to doing if you want to be a space-time functionist in that sense? Well, you're going to presuppose that there's something like a common cluster of roles for space-time in previous theories. You're not going to suppose there's one role, you're not going to suppose there's once and for all, you're not going to suppose it can't change. You're going to suppose that one of the things you might want to do is look at theories that we think we understand reasonably well, like general relativity, and understand how we're using the space-time concept in that theory to see what we should say in new theories. And it's really important that anything we're going to say about the space-time concept, we're not going to do as kind of armchair philosophers a priori, but there's something like a concept that we've built up through successive physical theories that's been really important and interesting, and it's something that we might be interested in as a matter of kind of scientific interest. And once you have a kind of sketch of the role, then you can go to a new theory perhaps, and you can look and say, look, there are structures in this theory that play something like the role in previous theories. So that's the kind of project I'm interested in. And that commits you to a careful look at physical theory. The only way you're going to do this is to look at our current theories and then look at maybe some sort of more pathological cases. Why be this kind of space-time functionalist in the really broad sense? Well, I mean, I mostly think you should do it because the alternatives are really bad. And I think when one thinks clearly about it, everyone's really a space-time functionalist, and then you and I can disagree about what the functional role for space-time is. But look, I mean, how would you not be a space-time functionalist? How would you think that how you go about identifying space-time structure and, say, a new theory is something other than looking at how it relates to the rest of the theory and the kind of role it plays? Well, one thing you might do is you might think, well, just mathematics is going to tell me in some very naive way. Of course, when you look at the role for space-time in your theories, mathematics is going to be involved, but you might think, oh, I just look for, manifolds and metric tensors and connections, and then I identify space-time structure. I don't think that's anyone's considered opinion, but you can certainly find bits of the physics literature where people do that, where they say, oh, we've created a space-time with X, Y, and Z properties because they've got some mathematics with those properties, and then you look at how it fits, and you think, oh, it's not quite right. So that's one thing that I think is not a good way to go. Another way you could go, not mutually exclusive, is you could kind of think that the trouble with giving any kind of functional analysis of the space-time concept is I'm going to have kind of lost the essence of space-time, the space-timiness, where somehow that space-timiness is definable in some way that's not about relationships to other things. So you might think that space-time is intrinsically containery, or like an arena or a background. There's some kind of metaphysical character to space-time, right? That's not capturable in a functional role. I can give some meaning to arena, background, container that is capturable by talking about how things relate to other things, but you might think there's something over and above that. I don't think that's a very promising way to go. I have no idea how you would apply it. I don't really know what it means. I think it's mostly metaphorical in as much as it doesn't have functional content. So I think that when you sort of contrast it with these sort of other ways of thinking about how you might go about this project, it's sort of obvious that something like functionalism is the right way to think about things. Right. So we haven't done very much of interest, even though I guess there's a long and illustrious history of philosophy, right? You just announce something's functional, and then you say absolutely nothing about what the functional role is. Maybe you say something like, pain causes you to say ouch. But I don't want to do that because I actually want to apply this to physical theories. So I'd quite like to try and say something about the functional role. So the whole point here is that maybe we can have a look at sketching, and say not sketching in a complete way, not doing this once and for all, but looking at how space-time behaves in current theories, and see if we can find some kind of guidelines for how you might spot bits of structure that are playing the same kind of role in future theories. So one of the things you're interested in is kind of finding what instantiates that role in another theory. And here's a rough idea I think is a good one, right? You say that the space-time role is going to be filled just in case something plays the role of a structure of inertial frames. Okay. So why might I think that that's a good thing to do? Well, you could put some sanity checks on something like a functional role for space-time. Even if you're an out-and-out operationalist, and I'm not particularly, but space-time, you should be worried about what space-time structure is. And one of those reasons is that in the phenomenological domain, we more or less read off empirical predictions in certain ways from space-time structure. Right? Space-time has a sort of automatic association with the behavior of important measuring instruments. Most experiments ultimately come down to measuring times and distances somewhere. Right? So as a minimal requirement, a kind of sanity check on your functional role for space-time, in a phenomenological domain, your functional role for space-time should be such that if a geometrical object instantiates it, then that object has its usual operational significance in terms of clocks and rods and light rays, and all the kinds of things you think might have kind of automatic geometrical associations. And if you want to make sure that's true, and I'll say a little bit about the connection to Harvey's work in a second, but we'll sort of start seeing Harvey Brownish, if you're familiar with Harvey's work, you'll see Harvey Brownish themes creeping in. In order to make sure that's true, then you had better think very hard about how space-time structure relates to dynamics. Because if you want stuff to behave the right way in space-time, then it had better be the case that the space-time structure is coupling to the dynamics in the correct kind of way. Okay. So this is where I think some thoughts of Harvey's are very helpful. So Harvey Brown and Oliver Cooley, some years ago, described a position that they called dynamical relativity, and then it was developed by Harvey in his book. This is one slide about a complicated position. But one of the ideas here is that a good shortcut to understanding the full complex behaviour of, say, a clock or a rod or something that can survey space-time is to think about the symmetry properties of the laws governing that matter. And if you understand the symmetry properties of the laws governing rods and clocks, you can predict their spatiotemporal behaviour. So if you want to make sure your rods and clocks operationalise a Minkowski metric, you better make sure they're Lorentz covariant. And it's all a little bit more complicated in general relativity, because it's going to become a matter of the dynamical fields coupling to the metric in the right way, but the strong equivalence principle is going to express the relevant property of matter fields in general relativity. Now, there's lots of different philosophical strands in this dynamical relativity, and I don't want to pick up on all of them. But one way of thinking about the kind of project that Harvey's engaged in is thinking about, so Wayne wrote a nice paper about this, and he talked about thinking of it as doing the kind of unfashionable conceptual work I was alluding to in the last couple of slides. And I think that's a good way of thinking about kind of one of the things that's going on in dynamical relativity. One thought behind dynamical relativity is that in special relativity and general relativity, the claim that the metric represents space-time structure just amounts to the claim that the dynamics picks out a certain inertial structure. There isn't conceptual space between saying space-time is Minkowskian and saying all of the fields are Lorentz covariant. Those are sort of two sides of the same coin. It's one way of thinking about one of the laws of dynamical relativity. And I should say that I think you can decouple that to some extent from some other claims about orders of explanation and perhaps about the substantiveless relationist debate. And so I just wanted to pick out that one strand. Okay. So that kind of gives you a hint as to how you might go about describing something like a functional role that would ensure that space-time had the right kind of relationship to matter. In current theories, that kind of basic phenomenological desiderata of doing the right thing with respect to rods and clocks is going to be satisfied if we say that the space-time role is satisfied just in case, by some object, just in case it specifies a structure of inertial frames. Where I want quite a thick definition of inertial frame, I want quite a lot to go into it. They're not just the frames in which freely falling bodies move in straight lines, but they're also the frames in which the non-gravitational interactions take a universal simple form, and in which freely falling bodies move in straight lines. And so you get this kind of appropriate connection built in to the dynamics, because they're the frames picked out in some sense by the dynamics. In the relativistic context, if I hand you inertial structure, you get conformal and projective structure and you get full metrical structure back for free. And one really simple way of seeing that is that if you think about the Fermi normal coordinates and you know them everywhere on the manifold, right, in ordinary GR, then you just know the metric, because you know the value of the metric in the coordinate system on the manifold. So inertial structure kind of has enough structure to pick out the kinds of geometrical things that we're interested in. Okay, so that's a proposal for a kind of functionalism. Not everyone likes it, which is fine. There might be other ways to do it. One of the reasons people don't like it, though, I don't think it's a very good reason. So one of the reasons people don't like it is they go, ugh, coordinates. Coordinates are yucky. We learned that we hate coordinates. Maybe something if any of the things I say about non-commutative gravity are right, maybe I'll help convince you that we have to question that a little bit. But here's one thing that sometimes gets missed when philosophers do a lot of differential geometry and go very pure, very geometrical. They kind of miss the fact that we always use coordinates, right? You have to put things into coordinates to make predictions or to do physics, right? Ultimately, you can't get lots of very interesting predictions about what some planet system is going to do from coordinate-free geometry. The other thing is that, coordinate, and there's this nice paper by David Wallace that maybe some of you have read, who's afraid of coordinate systems that sort of basically just says, look, there's another way of thinking about geometry that's a coordinate-based way, where you think of a kind of Kleinian conception of geometry and you think of it as about the kinds of symmetries that are expressible in coordinate transformations, and that's a kosher way of thinking about geometry. And it's just again two sides of the same coin. So I don't think we should be frightened of a theory that tells you that some of our coordinates are kind of important. I think that's okay. I think that there's lots of structure in coordinates. One thing you should note is that when I say that sort of whatever sort of defines the structure of inertial frames is going to count as space-time, that's a sort of shortcut. And I don't say it's really not once and for all, so it might well be. It's in relativistic theories at least, it's a way of bundling together a whole bunch of things that space-time does and kind of finding a way of finding the structure. It might well be that in future theories, lots of these different roles that space-time play come apart, and you have to kind of track things in different ways. Okay, but I think it's a pretty plausible one, in part because the history of the space-time concept and inertia are very intertwined, right? So, I mean, even in Aristotelian space-time, if we could talk about that, we have something like a notion of inertial motion. If you want to work out what we think about space-time in Newtonian mechanics, whether you think that the correct space-time structure for Newtonian physics is neo-Newtonian space-time or Newton-Cartan space-time, either one, the thing that's going to get you there is consideration of the correct inertial structure. And inertial reference frames are also going to be the key to the structure of Minkowski geometry, in that if you know the full structure of inertial frames, right, and you know that they're related by the length transformations, you have the Minkowski geometry. And in general relativity, even though people think this sort of instantiates general covariance, which of course it does, inertial frames are still associated with the Fermi normal coordinates of the metric. So at the origin of those Fermi normal coordinates, right, the connection coefficients vanish and the metric takes its Minkowskian form. And so you have this kind of privileged class of coordinates in general relativity, in this particular sense, in my sense of inertial coordinates. And the reason you get that is just because of the strong equivalence principle. Right, so that, I take the strong equivalence, I'm not going to, I mean, one can write a talk about the strong equivalence principle, but I'm not going to try and sort of define it, because assume we all sort of roughly know what it is. But I take it that all I think the strong equivalence principle does is express that feature of general relativity that means that the matter fields are well adapted to the metric. So, however you want to phrase the strong equivalence principle, it expresses that feature of the relationship between the matter fields and the metric field, such that systems built of the matter fields reflect the geometry of the metric fields. Things in my hands. Okay, so that's the sort of, I mean, probably think it's quite speculative, the less speculative part of the talk. What I want to do in the second half of the talk is to try, and so just pretend I'm right for a moment, and this is a helpful way to, or like grant me for the sake of the argument, this might be a helpful way to think about things. I want to try and apply some of those morals to a particular kind of quantum gravity. And I mean, to be completely honest, the only reason I'm thinking about this kind of quantum gravity is because, as you'll see, it turns out there's kind of some models in it that seem to work pretty well when I say Fermi normal coordinates turn out to be really important. So it's a bit cherry-picked. So I should fully confess that it's cherry-picked, but it turns out to be extremely interesting in its own right. Okay, so this is the part where I'm going to give a kind of sketch, and half of you, 3/4 of you, all of you, will know too much for the sketch, and then who knows if it will be helpful for the others, but maybe at least it will reveal if I'm making any mistakes or have any confusions here. Alright, so reasonably familiar to all of us, right, that ordinary milieu differential geometry can be given an algebraic formulation. It's the kind of thing that Bob Garrett did in 1972 with his Einstein algebras. Right, you have some set of scalar fields, the infinity, or a relevantly related ring in the Garrett case. The algebra, and you get back topological and differential structure from the field structures, and you can describe other aspects of differential geometry algebraically. So, vector fields are represented by the class of derivations, which are just the automorphisms of your algebra that satisfy the Leibniz rule. A metric turns out to be an appropriately symmetric isomorphism between D and D star. Right, so I mean, I'm not going to do the details there's nothing going to be mathematically detailed about this. But the basic point is that you can have an algebraic representation of differential geometry, and it's completely dual to the differential geometry in the ordinary commutative case. You can set up all of the same structure that we normally set up on a manifold in these algebraic terms. And indeed, you can prove representation theorem between the two things. If you can do that with ordinary geometry, then, and you like playing around in mathematical space, it's obvious to ask what would happen if you set up an algebra, but the algebra was non-commutative. So you can define an algebra, and so now at this point, right, you know, there's this sort of interpretational move you can make, where you think about the algebra on the previous page. You stop thinking about manifolds and points, and you just think of the elements of the algebra as usually kind of abstractly defined by their own place in the algebra. So now we're going to move to a kind of geometry which doesn't have any of the natural point associations at all, but we can sort of think of it by analogy to our commutative geometry. So we define some new algebra, r d theta. In this case, theta is a non-commutativity factor, and d is that's sort of the number of elements. And you're going to say that coordinates and polynomial functions of coordinates no longer commute under the product structure, right? So if you're in 2 dimensions, by the way, I mean the hats, they are operators, but and this is somewhere where I'm sure I can be confused and people can correct me, but I think everything I'm doing is completely on quantum. And I think there's a way of doing all of this where I don't get into the messy question of how this relates to algebraic field theory. So hopefully I'm doing that. So don't let the hats disturb you. But so in 2 dimensions, I could have some x coordinates and some y coordinates, and they have a commutation relation, right? And then I just define vector fields and differential operators and metrics and everything else in the same kind of way, an analogous way to how I would have done it in commutative geometry. Not that much changes, right? And one of the things and then I could define a particular non-commuting geometry by placing some kind of constraint on my non-commutativity factor. And in the standard case, you define this thing to be a constant real value down to symmetric matrix, which turns out to be relevant later. And all of that's perfectly algebraically well defined, but it has no complete natural mapping back into the manifold structure. Right? There isn't a duality between this and familiar manifold geometry. But if you want to do physics, one thing to say also is that you've got enough structure here that you can do, there's a sense in which you can do physics in this, right? You can write down Lagrangians and you can do dynamics and everything else. But if you really want to do physics and you want to have any idea what the empirical consequences of this stuff might be, or how to get the whole structure working, you actually want to map it back into a commutative space. So you can map your non-commuting algebra back onto the commuting algebra via this thing called the Weyl transformation. And what you end up with is a kind of representation of the non-commuting algebra on the manifold. But you've got to be really careful about what you're doing when you do that, because what you're doing is you take each element of the non-commuting algebra and you map it back to an element of the commuting algebra. Right, but that doesn't mean that that doesn't obviously mean that these things aren't isomorphic, right? So you're going to introduce various distortions. But you get a representation of the geometry of your non-commuting algebra on the manifold. And one of the ways that you can see that you're dealing with a non-commuting geometry is that when you Weyl transform everything, you don't end up with the normal product, but you end up with this Weyl star product, and it introduces a non-commutation factor anywhere you have a product. And, I mean, the next couple of slides are where I just have a hard time getting my head around everything. But the dynamics of the theory involves the Weyl star product and not the ordinary product, and as a result, the dynamics doesn't generically respect the commuting geometry to which it's mapped. Now, the obvious question is, what the hell does that mean? What does it mean for a dynamics not to respect the commuting geometry into which it's mapped? It's kind of language you find in some of the books. One thing that gets said, and that seems to be true, is that these theories fail to reflect the diffeomorphism covariance of the theory that we map them into. So this theta factor is defined as a constant antisymmetric matrix, and it's not invariant under ordinary commutative coordinate transformations. You can't just transform it in ordinary ways. But the dynamics all involves theta, right, and all uses the Weyl star product. And theta turns out only to be constant with respect to a privileged class of frames. Which is kind of a weird thing. And one way to note what's going on here is that if you think about the class of homomorphisms of the non-commuting algebra, they generate a subclass of the diffeomorphisms of the manifold of the homeomorphisms of the commuting algebra. So if you take a representation in the manifold space and you map it back into the non-commuting algebra and you perform a homomorphism on the non-commuting algebra and you map it back, the transformation you've induced on the manifold will be the set of transformations you can generate that way on the manifold will be a subclass of the diffeomorphisms, not the full diffeomorphism set. I mean, in a sense, this wasn't really ever meant to be the point of the talk. I just wanted to talk about Fermi normal coordinates, but so at this point, when I tried to write this talk too late without enough time to think hard about this stuff, I got really muddled about general covariance, and I'm still deeply muddled about general covariance, and maybe some of you can help unmuddle me. It looks like this is a theory that cannot be written in generally covariant form. And certainly philosophers, and I assume quite a few physicists as well, have often taken on board the Kretschmann objection, 1917, to Einstein that said, look, you know, there's no such thing as substantive general covariance, because anytime you have a kind of spatiotemporal theory, you can always write it in generally covariant form. You've just got to introduce more explicit geometrical structure. And that looks like it's true for, you know, Newtonian mechanics and relativity and pick any reasonably well-defined theory on a space-time that we're familiar with. It looks like that more has been true. And lots of different things are meant to different people by general covariance, but it's sort of hard to know how you square that with something that people working on commutative geometry say, which is the theory isn't generally covariant. And I think what's going on is that this theta mu nu just doesn't have well-defined transformation properties under arbitrary coordinate transformations. So because you can kind of only generate a subclass of the diffeomorphisms in this kind of natural way, it's not, you simply really know what theta mu nu looks like in a certain set of coordinates, but you just don't know what it looks like in other coordinates. Does that make sense? I don't even know if that makes sense. I mean, I do think that the usual techniques for generating generally covariant formulations, right? I mean, normally this kind of algorithms, right, by which you should be able to get out the generally covariant form of a theory if you just know the coordinate transformations. But you start by knowing how to write your theory in different coordinate systems. And so if you just don't have a clue what you're doing, I don't know how you get off the ground. So, I mean, take this as a giant confused slide. This is my confused slide. I welcome people who can confuse me. Or maybe I'll just confuse all of you too. Right. So, maybe this theory isn't generally covariant and can't be written in generally covariant form, and that's really weird. What does certainly seem to be true is that these theories generically induce privileged coordinate systems in the manifold geometry. So there's this. So one of the reasons I sort of started looking at this was there's this little paper on the archive by these guys that takes a model of canonical non-commutative gravity as an SO2 gauge theory, and does some stuff that sort of turns that quite a few people do in this literature. So they show that non-commutativity can lead to curvature and torsion in these kinds of models. So the kinds of geometry that you induce in the manifold, if you like, if induce is the right word, it's sort of how I think of it. Right, you've got your fundamental non-commuting geometry, and when mapped into the manifold, you have certain kinds of objects on the manifold. And those objects on the manifold are going to have curvature and torsion. So if you start with Minkowski geometry and take a kind of perturbative approach to finding, sorry about this line by the way, it's not my computer, I don't know where it's coming from, to finding the Weyl transform of the non-commutative covariant derivative of metric, then you end up with kind of perturbative terms for the torsion and curvature that depend on the value of theta. So it looks like if you turn up the non-commutativity, you turn up the curvature and torsion in these kinds of theories. So that's, I think that's sort of standard, and shows you why, right, you might think this is an interesting route for coming up with a theory of gravity, because it looks like you've got this sort of thing in the non-commuting geometry that's going to lead to gravitational effects in the kind of induced geometry. But the other thing they show, which is really kind of interesting, is that the coordinates, with, what look like pretty minimal assumptions to me about just natural ways in which you might write down a theory in this, you end up with the idea that with theta being constant with respect to a privileged class of coordinates that are the Fermi normal coordinates of the induced metric. So the reason I think that's interesting is because this seems like a funny little case in which something like the kind of, what I think of as some of the core of the content of space-time geometry kind of pops right out of the attempt to map this super weird thing onto ordinary space. That seems kind of intriguing. And obviously it also just makes Fermi normal coordinates look really important. That's something I like to say. So that's, it's always nice when somebody randomly writes a paper that agrees with your philosophical preconceptions, and you can cherry pick. Okay, so that's sort of why I got interested in sort of thinking how to turn these words on this stuff, turn me onto that paper, and I thought, oh, this is intriguing, and then tried to understand non-commutative geometry. Didn't succeed terribly well. But even if you're not interested in some of these details, one thing you certainly do generically have in these cases, and this is actually pretty typical in lots of different kinds of scenario you might have in quantum gravity, right, is that you have a kind of too many geometries scenario. You have all these geometrical objects, all this stuff hanging around. And you might want to say that there's, which one of these things are space-time? It's really part of the question. So you've got the fundamental non-commutative algebra, you've got an induced affine geometry on the commutative space, and that's given by covariant derivative of torsion typically in these theories. And one thing about a covariant derivative of torsion is that the structure that it induces on the manifold is not the same as the metric structure, if you have torsion. The geodesics of the connection of the metric reverts. You've kind of got one kind of geometry that's represented by the affine structure, you've got another kind of geometry represented by the induced metric geometry, and then you've got some set of preferred reference frames picked out by the non-commutative geometry, which in our particular case happen to agree with the preferred reference frame from the metric. Right? So you have some agreement in this particular case between these two things. But what you have is a whole load of geometrical structures, and you might want to try and say something sensible about them. This is the kind of scenario that kind of makes me think that we need to do this conceptual housekeeping. And in particular, the conceptual housekeeping becomes really important when you start asking the kinds of questions that both physicists and philosophers like to ask. Philosophers ask it at length, right? Physicists usually in the first paragraph of a paper on quantum gravity say a whole load of things about space-time, but nonetheless, people make these interpretive claims about space-time, and they're interested in answering these kinds of questions. Does the non-commutative theory involve space-time at all? If so, what you would say about it? Where does phenomenological space-time come from? Is this an emergent space-time theory? These seem like reasonable and good questions and the kinds of things that perhaps we ought to be asking. So the one point which I sort of think ought to be controversial, right, is that if you don't have something like a functionalist criteria for identifying space-time, it's really hard to know what you could possibly say in answer to any of these questions. You've got all of these competing geometries, it doesn't look like intrinsic mathematical criteria are going to choose between them. And I mean, some of you will have deeper and stronger metaphysical intuitions than I do, but when I'm presented with the kind of list of structures on the previous page, I don't get to go, oh, that one's the container. That's where we live. So my feeling is that we have to kind of have some kind of functionalist criteria to begin to answer these kinds of questions. And in this particular case, I think that inertial frame functionalism, this particular functional criteria, is useful. So here are some very sketchy answers to the questions. I'm much less attached to the particular answers to the questions than I am to the fact that this is the right kind of way to try and answer these questions. I haven't done anything like the kind of level of work on the theory that you want to do to have good answers to the questions. But yeah, this is the kind of ways you might answer questions in this. So, does the non-commutative theory involve space-time at all? Well, yes. There's clearly a privileged structure of inertial frames here, at least in the particular model we're looking at. So there's a sense, and inertial frame here, remember things shift around a bit, at least in the sense of the class of frames in which the dynamics take a simple universal form. The notion of a force-free body, non-commutative geometry, I don't know where to start. So perhaps you'll lose some of the content, but you've still got something very like a structure of inertial frames here. So I suppose you accept that there's something like space-time in this theory. What should you say about it? Well, one thing that's sort of intriguing about this theory is that I usually sort of read straight over, and I'm sure, I hope no physicist would be offended by this, right? The bit where someone goes, now space-time's grainy, or now space-time's foamy, or they say something that sounds extremely metaphorical about the nature of space-time based on their theory. And often I just think, oh, that's just, that's sort of just sort of the descriptive fluff around the theory. largely because I'm not really sure in what sense the, say, discretized structure that they're talking about really counts as space-time. But in this particular case, there seems to be some sense in which space-time itself isn't smooth, at least. So, at least in as much as, this is more tentative stuff, but at least in as much as it looks like the non-commutative geometry kind of directly picks out the structure of inertial frames. So you haven't got some kind of long emergent story from this sort of unspaced temporal looking structure to something that looks like space-time. You've got some kind of slightly direct picking out. So it seems maybe reasonable to say that the non-commutative geometry is spatio-temporal because it plays this role of picking out a privileged class of inertial reference frames. What about phenomenological space-time? Super important, we live in it, we do physics in it. Where does it come in? Well, I mean, this gets really speculative, right? Because I take it that nobody's managed to get general relativity out of one of these theories. So, I mean, but let's go into like the fictional world where this is all developed and someone's managed to use non-commutative geometry to derive some approximation to GR in appropriate domains. I assume that what we're trying to do, and the reason why we care about, say, non-commutativity being a kind of source of torsion and curvature, is that what you're looking for is that the metric that's returned in the commutative geometry would be the GR metric in some appropriate scale, right? And one of the interesting, so in this case, you do have phenomenological space-time, I mean, this is a very counterfactual sense. You do have, if you had that theory, right, you'd have something like phenomenological space-time coming out of the theory in the GR form. What's kind of interesting here is on this particular kind of theory, it looks like you might have a fundamental explanation for that structure, right from the fundamental theory, kind of in this direct way, because the fundamental theory privileges this class of inertial frames, and that tells you why the phenomenological metric structure is as it is. But that would all depend on the details of the theory. Another kind of intriguing thing, so I think so generically often gets lumped into a class of things people call emergent space-time theories. But another thing I sort of think is intriguing is that, I mean, obviously it depends on what you mean by emergence. Yeah, I give you a long description of what I think emergence is, but let's assume that emergence is a relation that holds between theories usually when there's some kind of pre-complex relationship between them, and there's lots of approximations and idealizations that happen when you move between theories. In that case, maybe you don't have an emergent space-time theory here. In our kind of fictional case, where we develop GR magically out of non-commuting gravity, the metric structure of general relativity maybe arises quite directly from the underlying non-commutative theory. So it's not a distant enough relation to count as one, an emergent space-time. There aren't the approximations or idealizations involved. So you have this kind of intriguing case where the underlying geometry is really different from the geometry of GR, but the relationship is in fact sort of strangely close between the two theories. Seems kind of intriguing. So that's more or less all I have to say. As I say, end of that, extremely speculative. Please disagree. I mean, as I say, lots of that's going to depend on details of how these theories work out. But the real point of all of that was just to say that look, this kind of way of thinking about things, this kind of looking for certain structures that play a functional role in the theory, is a really good way to get on with the business of trying to answer some of these foundational important questions. And in this particular case, at least, inertial frame functionalism provides really interesting answers to the questions, or hope with interesting answers to these kinds of questions. And it's hard to see how any non-functionalist theory could tackle those kinds of questions in a kind of coherent, conceptually tidy kind of way. Also, the other tentative thing, which was, as I say, wasn't originally supposed to be part of the point of the talk, but has ended up puzzling me so much, I sort of wonder if the existence of this kind of theory just has to make us, means that we should go think really hard about what general covariance is, what it means, and under what circumstances you can reformulate a theory